right, cool. All right. Hello, my name is John Hammond. I am a graduate student, computer science major. Today for my final project, I'm going to be presenting on a chess ELO predictor. So given a chess game, I want to try and guess the ELO of the average ELO between the two players. So just as a quick little background, chess is a turn-based strategy board game. So it's played, of course, on this board, entirely on this board. Turn-based, so white moves and black moves, etc. Strategy, there's not really any luck involved or anything. It's just purely between the two players. Two players against each other. The possible results are one side wins, or you win, you draw, or you lose. So it's a zero-sum game. Anything that one player might do is a good move that one player makes is bad for the other, and vice versa. Just as a load of quick facts about the history, it originated from India in about 600 AD. From there, it spread throughout Asia and Europe. Of course, the rules did change over these 1400 years, but the rules mostly settled into chess as we know it now in about 1600 AD in Europe. The actual rules don't really matter too much. Like understanding how chess works isn't required for this project. But the idea is that, but just as a quick little background, you have different pieces that can move differently. So you can see in this previous picture, you have a king, queen, bishop, knight, rook, etc. Each of these can move in a unique way. For example, you can see here a bishop move diagonally and will move diagonally. You can capture opponent pieces. You can force a move. So if you attack the king, they are forced to move it. There's a bunch of other random little rules that aren't super important for this project. But the goal, in order to win, is you have to both trap your opponent's king and you have to attack it. So if you attack your opponent's king, they have to move it, which is a check. But it's checkmate if you attack your king and your opponent's king and they can't move it. And obviously your opponent's trying to stop it, and at the same time, checkmate your king. A little bit more about chess. Nowadays, chess is mostly random computers. This is because chess is turn-based, so looking ahead is super, super important, and being able to, hold in all those different positions, being able to calculate far ahead is super important to be a good chess player. In 1997, the first computer beats the world champion, the best human player in chess. This, of course, was Deep Blue by IBM. It beats Garry Kasparov, the world champion, and pretty much undisputed best player in the world at the time. And that was 3.5 to 2.5. So it was still pretty close. But of course, a win's a win. And nowadays, computers are considered to be much, much better at chess than humans. A lot of the chess bots they might see like on chess.com or whatever, they purposefully don't give it the best resources that it could have. So they program in, like sometimes they make wrong moves, or sometimes they purposely only like search ahead 5 moves instead of the normal 20 or whatever. And computers are so much better that the best human could play the best computer like 1,000 times, and they'll never win even once. Just because computers have been so optimized since then, both in hardware and in software. So, of course, these chess computers, the most important mechanism for how they work is how it calculates evaluations, how good a position is. You might remember from the min-max algorithm, alpha-beta pruning, that one of the very important aspects of that is being able to assign some number to how good a position is. So that way you can only look at the better positions. So, of course, I have some examples down here. On the far left, you can see that white is pretty clearly winning. You don't need to have a computer. You don't need to know anything about piece value for that. Just physically, there's so many more pieces than black does. Same thing on the far right. Black has way more pieces than white does. So, of course, black is very, very heavily winning. these numbers on this bar on the left side of each of these boards, these are the evaluations. Of course, this is 19. You might see it sometimes as plus 19, as in white's favored plus 19 by 19. Here it's on the black side, so you might see this as minus 20, so black's favored by 20. This number represents can be about correlated with the piece values. So, for example, pawn's worth 1 point, knight's 3, etc., etc. So, for example, if you're up, if you haven't if you've captured your opponent's knight and pawn for free, and your opponent doesn't capture any of your pieces, you'd be up 4 points. That's what these numbers represent. But in the middle is a little bit more of an interesting board state. So you can see that black is up 2 pawns. White's captured 1 of black's pawns, whereas black's captured 3 of white's pawns. So normally you think, oh, they're plus 2. And that's what this number up here is. It's the mature value, it's plus 2. But actually, it's not quite that simple, and computers do a lot more than just looking at piece values, of course. So here you can see it's actually only plus 0.5, or only plus a half. So despite being up 2 pawns for free, it's only up about 0.5 or half a pawn. This is because it also factors in the position. So here you can see, if you know the stuff about chess, these bishops are really, really well placed. White has a really easy time developing their pieces, whereas black still has a lot more time to get their pieces out. So of course, having a better engine or having a better way of evaluating means that you can your bot would be better. I think it'll try to get into better positions more regularly, and it'll be able to calculate faster as well. So you don't have to go to such so you can calculate through more depths. Now in competitive chess, mainly a human thing, the chess ELO is defined as the ELO rating system measures the relative strength of a player in some games, such as chess, which is what we're doing, compared to other players. So it's a way to assign a number to how good a player is. So of course, if you win, you'll gain ELO. If you lose, you lose ELO. If you win against a player who's higher rated than you are, you'll gain more ELO. Whereas if you lose to a player worse than you, you'll lose more. And vice versa. If you win versus someone who's lower than you, you'll gain less ELO. And if you lose to someone who's higher rated than you are, that's more expected, and you'll lose less ELO. I think these numbers are from chess.com, but in Blitz, for example, highest rated is 2971, so somewhere around like 3000s range, and then the lowest is 600, but different sites have a different lowest. At that point, if you lose any, you just stop losing ELO. It's just like a hard floor. Whereas the ceiling does not have any limits. Here you can see, just to get more of a general idea of what ELOs look like. I think this is for Rapid on Lichess. Looks like Lichess goes from 400 up to, looks like highest rated somewhere around 2,800. But you can see that it's not symmetric, it's not uniform, it is skewed. Looks like the center is around 1,400, 1,500, and the majority of players are between about 1,000 and 2,000. So our goal is to be able to guess that. Yeah. The goal is to, given a list of players' moves in a game, I want to predict the average ELO between the two players. So some related work, for example, chess.com actually does have, after you run an analysis on the game, you do have to pay for premium or just have the one free one. But it does give you a prediction of the ELOs. That is, though, considered to be very inaccurate. Give me a second. I got something to call. Cool. Cool. All right. That is, of course, considered to be normally considered to be very inaccurate, and it's also very unknown of how the program actually works. I highly doubt that they actually use any machine learning tactics for that. It's pretty just all normal computations. But yeah, it's not considered to be very good at all. Also, the main, I guess, inspiration for this was Gotham Chess' I guess, the ELO. In this, Gotham Chess is an international master, one of the, I'd say, probably top like 1% players in the world. He also teaches chess a lot, and he sometimes takes in viewer games, and he tries to guess how good you are based on that, gives some analysis, etc. He's also sometimes is very inaccurate. It can be very inaccurate sometimes as well. That's because chess, a lot of time, it's not easy to guess ELOs, really. A lot of times, like a bad player can sometimes just randomly find a good move, and sometimes really good move players just randomly make a blunder that makes them look really bad. So that's when hopefully maybe our project we can guess it somewhat accurate, but it is difficult. It's not unlike like classifying like iris flowers or whatever. It's not determined. It's not like deterministic. We can't always 100% know exactly how good a player is. So for our projects, we will only be looking at rapid chess. So there's different time controls they can play. For example, you see here on the chess, there's like 1 minute, 3 minutes. This 3 plus 2 is you have 3 minutes to play the game, and then every move you make adds an extra 2 seconds. But we will only be looking at rapid, specifically 10 plus 0 chess. It's because different players actually play at different levels and different time controls. Some players prefer to play fast games. Some players are better at slow games. But generally, the ratings are broken up because they generally don't correlate very well with each other. So, for example, here in this graph, this is on Lichess. You can see specifically for like bullet and bullet versus classical, bullet versus rapid, where bullets is the slowest, rapid and classical are the two fastest one, or the two. No, sorry, bullet's the fastest time control, whereas classical and rapid are the slowest. You see that the correlation is not very good between the two. Obviously, they are just positively correlated, but it's not 1-to-1. Chess, Lichess, and every chess types do break up your ELO based on the time controls. So why did we choose rapid? It's better than bullet or blitz because there's higher quality moves. Of course, with the slowest time controls, we have 1 minute to play a whole game of chess. You're very, very prone to making errors unless if you're at the very highest level. So there's less variance, and hopefully we can get a better picture of how good a player is. It's better than classical purely because there's more games, there's less stagnation, there's less people just staying at an ELO and never playing again. Because classical is very, very long. You see 30 minutes, 30 plus 20. Classical can go for ages, and there's not a lot of games. So for our projects, we'll only be looking at rapid. We'll only be looking at games with more than 5 moves on each side, or 10 total. This is just because the small games really don't tell us too much information, and it can give us some very bad information. Of course, we're also only going to be looking at rated games because you don't want to be looking at classic game like casual games between friends or whatever. We only want to be looking at games where people are at the best, and we will also be using a uniform sampling of ELOs. So you can see here, ELOs are not uniformly sampled or not uniformly distributed. Actually tried to just toss it in without making it uniform. And that just ended up biasing it really, really hard towards the middle. So what we did was I grabbed 2,500 games of below 1,000, 2,500 games between 1,000 and 1,500, 2,500 games from 1,500 to 2,000, and 2,500 games from 2,000 plus to try and get more of an even sampling. So the uses for this, some motivations. Chess.com has many, many bots, and sometimes the rating on them are very infamously very, very poor. Here's an example. Nelson bot is rated at 1,300. I don't think she should really be at 300. I think she maybe like more closer to 1,200, but yeah. Also, when you start a new game, this isn't me, by the way, but if you start a new account, take some time for your elo to actually catch up to what it actually is. So maybe with this, you can get better. You can get to a closer elo of where you actually belong faster. Cheating detection 2. If a player suddenly plays at a much higher level than they normally do, that's can be indicative of cheating. So it could maybe help with that as well. Recently, there's been a lot of news and scandals regarding cheating online chess and over the board. All right. My data set, it came from leechess.org, which is huge thanks to them. I took the most recent month, April 2025, which was about 30 gigabytes, 91 million games. Obviously, I didn't use all of those. I cannot parse through all of those. I only took the first 10,000 rapid games, as we talked about. They're in PGN format, which means protocol game notation. So you can see it gives a bunch of metadata, the event type, the names, the results. What we're mainly looking at, though, are the two ELOs. We're going to be averaging these together. The opening time control, because we want to do the rapid games, and then the force the moves. Yeah. So yeah, like I said, so the first time, my first attempts, I just tried to input the moves. So the only features I added were just these moves. It didn't work out very well because it needs to actually be able to understand what moves are, so which essentially is an LLM problem, which doesn't, which I can't really do at home. It also doesn't respect move order. There's a huge difference. Move order really matters in chess, and you can't really do that without transformers or attention. So I had to skip that. So instead, I chose different features from the game to input, which I do think makes it slightly worse, more arbitrary. So of course, but it's just more realistic for projects. So these features, I ranked. So first, throughout the chess game, I ranked the moves. So for example, the engine would give out 3 top different moves, and then I found the percentage of the top engine moves that the player found, the percentage of number 2 moves, number 3 moves, etc., etc. I could only do this for the first 30 moves though, just because this does require hooking up Stockfish to my model, which does take a lot more time, and it's not really realistic to for me to at least analyze the entire game. I also looked at whether or not the player's castled, the number of moves towards the center, number of development moves. The idea is that a good player would maximize those moves. The number of checks, actually, it's kind of the opposite. Generally, you see a lot of checks at the lower levels. Average distance moved. The hope was that good players would move pieces further. Whether or not that actually is true is unknown. The opening classification. So different players play different open. So different ELOs have different common openings. So my hope was I could figure out something based on the openings. And of course, when we want to output is the average ELO of the 2 players. So the first algorithm was linear regression. Of course, it's the fastest and the easiest. Essentially just finds optimal weights for this equation. Of course, X here is our inputs, the vector for all the features. This will be some matrix. In this case, actually also a vector of the same size as X, just transposed, because we want the output to just be a single number. We have some bias and some error as well. So as an implementation, this is actually really easy using sklearn's linear model. You can see the whole linear regression is just a single line. Yeah, I use an 80-20 split between test and train. And as you can see, it's decent. It's not what I was hoping for by any means. This is, of course, the first graph. It's actual ELO, and this is the predicted ELO. Of course, with 10,000 games, with an 80-20 split, there's 2,000 testing points. The mean absolute error was 301, so that means that on average, we're about 301 ELO off. So if I guess it as, say, 1,000, on average, the actual one would be about between 700 and 1,300, which actually speaking isn't too bad, but it's still not what I was really going for. R squared was 0.7353. We want, ideally, we want that as close to 1 as possible, but you can see from the graph that there is some correlation. I would say this is positively correlated. It's just not as close to the line y equals x as we would hope. Second one, algorithm, is k-nearest neighbors. So the idea behind this one is that given a new data point, say this one, we'd find the k closest points, and that's from the train set, and we'd sample across those. So here k would be 5. We find the 5 closest points to it, and we would sample across those 5 points to classify the new points. In this case, there's 3 blue ones, just 2 red ones, so we call that blue. You could sample it. You could also just say the majority is blue, so we also classify this as blue. It depends on which one you're using. In this case, I choose k equals 10. It is somewhat arbitrary. I was playing around with it, and it looked like this one was when it stops. So it stopped improving. I just went up and up until it stopped improving. Again, sklearn.neighbors. It was super useful. You can see here, it's just, again, single line of code. Neighbors equals 10. Again, it's the same 80-20 split. And it's actually worse. I was kind of expecting this one to be better because k-nearest neighbors is nonlinear, and generally linear is tend to be not more simplistic, but for some reason it looked like this was worse. Mean average error, the mean absolute error, 324.13, R squared is 0.2577, which is less. Again, it is still somewhat positively correlated. But you can see that it's just not being very, I guess, brave. It's still trying to predict it very close to the mean, and it's not really, for some sample like these points out here, they're just way off. On the extremes, the guesses are very, very close to the mean. It's plain and safe. So the last model I used was a multi-layer perceptron. I think it's one of the more complicated ones that we learned. So fingers crossed, it would be better than the others. Of course, it takes in multiple inputs through different layers and outputs a vector. In this case, of course, it's the outputting scalar because we still want to have that one ELO guess. But yeah, you can think of getting layer to layer as just matrix multiplication. So I was playing around with this a lot. Of course, we have one input vector, which is the features. I just tried 6 hidden layers, 1 output, and 1 output layer, of course. Of course, the size of the first layer is just the number of features we had. Then again, these numbers are very arbitrary. I was just playing around with it. And this was the best model I could find, somewhere around 2000s. And of course, the last one has just 1 number in it. I did weight it, which you can actually see up here. Weights equals this thing. So this gives more value to guessing the points that are further away from the mean. So like higher ELOs and low ELOs correctly, and it penalizes for guessing those wrong more. And I did this over 1,000 epochs, but it wasn't actually 1,000 epochs because I used early stopping with patience equal to 50. Again, these numbers are completely arbitrary, but I found that this did give the best results. Higher patience did tend to lead to better results, and batch size of 2. Yeah. So you can see here, this is better than the other models by about 40 or 30, 40, with an MAE of 269.05, R squared is 0.52. Again, this still isn't exactly how I wanted it. I wanted this to be better, but again, what can you do? You can see from the data that it is clearly better than the others. It's this weird parallelogram shape. You can see that low ELOs are guessed to be pretty low, and high ELOs are guessed to be high. However, high ELOs are still being underguessed, and low ELOs are being overguessed. The middle, though, is pretty even. Here I plotted over each epoch. It looks like with the early stopping, it stopped at 120 epochs. Yeah, the blue is the train loss. It goes down. Validation loss does start to get in the middle. This is indicative of overfitting when the training loss goes down, but the validation loss does not. which probably has to do with the massive model that I used. But yeah, the results are still pretty decent, I thought, with this. Some improvements. As I was working on this, I was thinking that there are tons of things that I can improve. Mainly, you can't use too much data. You can also use more varied data. So what I mean by that is you can add more features. Again, the features I added were completely arbitrary. For example, we can look at you can actually factor in time because some of the games do include the times. We can also, for example, players make better moves if they have a lot of time, worse moves as it gets later on. So we could factor that in. Having one game from each player isn't very indicative of their skill level. In theory, we could group it by their players and get multiple games per skill per player. And the way I was classifying the openings, it wasn't great. I just assigned I kind of manually assigned different levels to each of the openings and just give each of those numbers, but has to be a better way of doing that. Of course, better evaluation. Again, I only analyzed the first 30 moves, so I could do longer of that. I could do it at a deeper level. I think I only did level equals 8, I think, for Stockfish, whereas normally you do it like 20 at least, for good evaluations, but I just don't have the time for that or the computing power for that. And then, yeah, like I said, evaluation based on time, maybe give players more leeway for if they're short on time and less if they're like at the beginning. So references, chess history, chess. The idea again came from Gotham Chess. Appendix. Yeah, pretty standard packages, pandas, matplotlib, numpy. sklearn was absolutely huge, and TensorFlow for sklearn was for projects 1 and 2, the linear regression and the k-nearest neighbors. TensorFlow Keras was used for the multilayer perceptron. Very useful packages. Again, database came from Lichess. It was completely free, which I really appreciate, and it was very easy to download. And the code will be attached to the submission. Thank you.